Hey guys, so today we're going to talk about 4.2, which is translations of the sine and cosine graphs. And I'm screen sharing with you the notes because I'm going to reference them a lot. And I'll probably leave up the front page after we get through the first two examples, it looks like, because the first two are pretty basic. But as they get a little bit more complicated, I might try to leave the steps up if I can. I did want to address that the information here is very similar to the information in college algebra from chapter 2, section 5. So if you've taken college algebra, then some of this should be review. Actually, all of this should be review. And if you haven't taken college algebra yet, then I wanted to encourage you to go on to my YouTube site and watch one of my lectures from either my Missouri Southern college algebra class or my Pitt State college algebra class. I'd say my Pitt State one's probably a little bit better done just because I used like this setup where I was zooming and recording versus using the Elmo, which I've noticed has a little bit of like double take on the sound. But either video would show you some good information about translations with functions. I also wanted you to note that in Pearson, in the My Math Lab site, when you open up your e-textbook, you actually have access to the same college algebra textbook that we use in college algebra. And if you go over to the table of contents and you click on college algebra, you can click down on chapter 2 and go to 2.5. And you can actually look through all the different translations of functions information. Like there's a vertical translation. We're going to talk about that today. And then there's going to be horizontal translations, and we talk about that. There is, hold on, let me skip ahead. On one of the pages, there's a really nice table where it shows all of the translations all together, which I think is super helpful. So this is a summary of the translation. So this is a good one. That's a good little table on page 137 of the college algebra textbook, where it tells you a general form of vertical translations and what that means for the graph, or the horizontal translations and what that means for the graph, or reflections. We kind of saw a little bit of that in 4.1 when we had our amplitude out front being shifted around. That's the vertical stretching. That's right here. See, they even use A just like we do. Horizontal shrinking, they used a C instead of a B. We use B in trig, but that's okay. But it's the same type of shifting. So in 4.1, we did vertical stretching and shrinking, which affected the amplitude and how high up our graph went or how much it got smushed down. And we also did horizontal stretching or shrinking, and that affected the period of our graph and how much horizontally it got stretched out or shrunken in. And so today we're going to spend 4.2 talking about vertical and horizontal translations. So just wanted to point that out, that you do have access to the college algebra text. And it's got some really good information in there for you. And maybe playing around with it with polynomials and algebraic equations will help it to click for the trigonometric functions that you're going to be messing around with. So all of that to say, today we're going to talk about horizontal shifts and vertical shifts. So horizontal shifts, if you look at the very generic function layout that they have here at the beginning, it says x minus d and x plus d. And notice that those happen inside of the function themselves. That's kind of a key component, is that if you have a translation happening inside of the function, like our horizontal shifts, or from 4.1, when we did those, when we had b in there, you know, it happened right there in front of the x, and that affected our period. Both of those happened inside of the function, and both of those impacted our x values. And that's key. If it's inside the function, it impacts our inputs. X is our inputs. Our vertical shift, if you notice, is the c value tacked on here on the outside. Happens on the outside of the function, just like our amplitude happens outside of the function. And if it happens outside of the function, then it affects your outputs or your y's. So that's kind of a nice mnemonic to kind of try and remember so that you know exactly what you're shifting and which way you're shifting. So the other nice, I don't know, nice, but the other kind of trick for these different types of translations is that if it happens inside of your function and it's affecting your x's, like your horizontal stretching and shrinking, which is with your period, or your horizontal shifting where you're moving the entire graph left or right, what it does is kind of the opposite of what you would think. So here, if we have x minus d, if we think minus, we immediately think go to the left because that's where the negative numbers are, but we're going to do the opposite. We're going to move to the right. And the reason for that is because really the general format for this translation is x minus whatever your d value is. So if your d value is positive, then it looks like x minus d. But that positive d value is where you shift to the right d units. Over here, I kind of expanded it so you can see what I'm talking about, where the general form is x minus, and then if your d is negative, you're shifting to the left. I think this is a little bit confusing here with my negative, and so I usually just try to teach students that if it happens inside your function, it's going to do the opposite of what you think. And we saw that in 4.1 with our amplitude, or not our amplitude, excuse me, with our period, because remember to find period, it's 2 pi over d, or excuse me, b. And if our b was say 2, and it's 2 pi over 2, then that made our graph shrink in, which is kind of opposite of what you think if you think about changing your period by 2. But what happened is because we divided by that b, it made our graph shrunken in. Whereas if our b was a fraction, like a half, then when we take 2 pi and divide it by the 1/2, it actually stretches it out over 4 pi. And so it did the opposite of what you would think. And the same thing is true here with our horizontal shifts. Our horizontal shifts go the opposite direction. So if it says minus d, you're going to move to the right d units. And if it says plus d, we're going to move to the left d units. The other thing I want to point out is here with our vertical shift. Our vertical shift, because it affects our y's, it's going to do exactly what you think. So if it says if c is positive, we're going to take our whole graph and shift it up c units. And if c is negative, we're going to take our whole graph and shift it down c units. So that moves exactly the way you would think. I did want to point out, though, that with our trigonometric functions, the c is stuck out front. But if you reference your anything with college algebra, the vertical shifts are usually tacked on here at the end. Do you see that? And here's the reason why with trigonometric functions, they don't usually stick it at the end. If I have y equals sine x minus 3, and I write it just like that, a lot of you will think, okay, wait, if this is like college algebra, then this is telling me I have a vertical shift down 3 units. And so you could interpret it that way. Or you could say, okay, well, wait a second, that's saying sine of x minus 3, that's a horizontal shift where I'm going to move to the right 3 units. And so to help with the clarity of what's actually happening, if there's any type of a vertical shift, it's going to be stuck out front so that there is no questioning what we're going to do with that minus 3. It is 100% obvious we are going to do a vertical translation. We're going to shift our whole graph down 3 units. So that's a slight change from the college algebra, at least the way that we represent it. The other thing I'd like to use to point out here is how important those parentheses are. So pay attention to them. Because if they write it like this, that's telling me that I'm doing a horizontal shift. And when you are writing things, whether it be on the test or anywhere else, you need to be aware that those parentheses really are going to matter. Okay, let's erase that. So we've got horizontal shifting happening this time. We've got vertical shifting happening this time. And so I made this little table because I think it's really helpful as we move forward to think about the very general formats of our sine and cosine graphs, where we have y equals c plus a sine bracket b times x minus d, and then you have the exact same thing for cosine. But each of those letters tells us a different translation that's happening. The c, or I guess I'll go in order because it says a. The A is our vertical stretch or shrink. That's what we did in 4.1. That's our amplitude. That's telling us how much we're stretching up or how much we're squishing our graph down. Our B is our horizontal stretch or shrink. Notice that's right inside of our function. That's our period. It's telling us how much we are stretching or shrinking our period for our graph to actually occur in. The C, which is tacked on here out front, is telling us the vertical shift, where we take the whole graph and we move it up C units, or we take the whole graph and we move it down C units. And then D is again inside of our function itself, and that's where we take and it's a horizontal shift, where we take our whole function and we move it to the left D units, or we're going to move it to the right D units. So I think this little table is very helpful in identifying at least what translations are going to occur within our graph. Now, as we start graphing these, there's two different methods that we can use. The first method is very similar, or pretty much what we used in 4.1, where you find the interval over one period, and you do that by taking 2 pi divided by b. And they said to do, sorry, if I don't move around enough, the lights turn off. They say to use this inequality, where we have 0 is less than or equal to b parenthesis x minus d is less than or equal to 2 pi. So what this is doing is it's setting everything inside of our function, inside the inequality, with our 2 endpoints at the end to figure out what a period is going to be. Once you find out what the period is, you divide that period into 4 equal parts. Then you evaluate the function at those 4 different parts, plot the points with the given amplitude, which is the absolute value of A, and you connect your points. Method 1 is pretty much what we did on 4.1. And oftentimes we use that table where we started with our X, which was the different intervals that we had, and then we kept applying all the different translations as we moved down until our bottom row was always our outputs, so that we looked at the top row for our inputs and our outputs were on the bottom. So method 1 is great. I used method 1. We're going to do 4 examples today, and I used method 1 on the last 2 examples. And I'm using method 2 on the first 2 examples, because if your function is relatively simple in terms of what translations are happening, method 2 is actually a little bit easier, I think. Method 2 is where you think about, or you actually physically graph the basic mother function, or you graph a sine b of x, or a sine or a cosine of b of x, depending on if we're talking about sine or cosine. So we start with the basic one, and we examine the amplitude, we examine the period, and then we shift it. We do the shifting either vertically or horizontally, or both, depending on what our equation is actually asking us to do. This can be really nice, especially when it comes to the vertical shifting, because your period doesn't change. So the only thing that really changes, and your amplitude doesn't change, you just literally shift your graph up or down. So that's kind of nice for method 2. The only issue that you're going to probably encounter is if you use method 2 and you do some like horizontal shifting, is that your period may be, 0 to 2 pi, but you're shifting to the left pi over 4. And so you're going to have to be decent with your fractions and how you're going to shift all of these values to the left by pi over 4 units and things like that. Either one of these methods is totally fine to use. Your book, I think it does every single example in the lecture portion of the book or the notes portion of the book with both methods. So if on example number 1, I'm using method 2 and you want to see it done with method 1, open your book, go to 4.2, look at how they did it, because they walk it step by step through, and it's a really good process. Like I said, the first 2 examples, because they're dealing with very minimal translations, I'm going to use method 1. And there's actually not really anything for me to show you in terms of like on the board. I will probably use the board on the last 2 examples just because there's a little bit more to them. And as we move through the notes, remember, at any point you can pause to write the notes down more, or you can always print off my notes. They are there for you to use. Okay, let me zoom in a little bit. So here is the first example. And like I said, there's not really a lot for me to show you. So I'm just giving you the whole answer and everything right out of the gate. So it says graph y equals sine of x minus pi over 3 over 1 period. And notice the parentheses. Those parentheses are around the x and the minus pi over 3. So that tells me that I am doing a horizontal translation. And anytime I'm looking at a graph, whether it's trigonometric, or excuse me, not a graph, but a function, whether it's trigonometric or it's just a polynomial or a quadratic or whatever it may be, and I know I'm using translations, I'm going to make little notes to let myself know what kind of translation I'm doing. And so if you look beneath my equation, I have an arrow pointing to the right, that I'm moving the graph to the right by pi over 3 units. And so that is what I'm going to do. It is the only thing that's going on in this is a horizontal translation. So I did method 2, where I drew the original y equals sine of x first. And that's this dashed curve right here. And then what happens is since this is a horizontal shift, my y values don't change at all, but my x's are going to shift to the right by pi over 3 units. And so instead of starting at 0, I'm now going to start at pi over 3. And then instead of being at pi over 2, I'm now at 5 pi over 6. And so everything shifts just a little bit to the right. And so notice the graph stayed in the same shape. It went up as far as it was going to, and I still only cover 1 period because it says over 1 period. But having that dotted line, then I know, okay, I just need to move everything to the right by pi over 3, and there's my new graph. That's why I like the second method when it comes to basic transformations or translations. In my college algebra notes, when they're pretty basic like that, I do that. Even later on, whenever we're doing multiple translations, like especially if you watch my lecture videos, my very last problem that I do has like 3 or 4 translations, and I do it step by step. So I do one translation on a graph, and then I draw a different graph with the next translation, and then a different graph with the next translation, so that I can see exactly what is going on each time I do a different translation. Okay, all of that to say this was just a horizontal shift. The next one has 2 different translations that happen, but they still weren't super complicated. So I still did method 2. This says graph y equals 3 cosine of x plus pi over 4. And I didn't write it out, but it was over 1 period. So this one's got 2 different things going on. Notice it's got this 3 out front, and we saw that in 4.1. That is our amplitude, and that affects our vertical stretching and shrinking. And so amplitude is the absolute value of that A. And so that's the absolute value of 3, which is 3, which means we are going to stretch our graph up 3. Originally, it would only go up to 1. And so now we're going to stretch it all the way up to 3. That's what happens with that number. And then again, inside of our function itself, we have x plus pi over 4. So that plus pi over 4 tells me I'm doing a horizontal shift, and I'm shifting everything to the left by pi over 4 units. And so again, I thought this was a relatively basic function. So I started by just graphing y equals 3 cosine of x. I went ahead and applied that amplitude to the base function, if you would, so that I could see it, because then I'm only doing one translation after that. After I've applied that amplitude, all I'm going to do then is I have to do this horizontal shift again, where I'm shifting everything this time to the left by pi over 4. And so I like having that base function on there so that I can see exactly what's happened during that shifting process. Again, you can use method 1 on these. I think it's a little bit more involved, which is why I like just using the base function and then doing the shifting itself. One thing I want you to note is that if you ever are 1000% lost on how to graph any of these functions, you can always do the point plotting method. You can pick different values for X and plug them in. I would say, hopefully at this point, if you're in trigonometry, you're a little bit past that. And you can make more educated guesses on what to plug in for your X based on what you know sine and cosine should look like in their basic forms. But that could help you at least get started on what it should potentially look like. Because really method 1 is kind of like that. It's just that through the first step, you are finding out your intervals. And when you find out your intervals, that is a very educated X values. Like you're not just picking them out of the air. You have algebraically found these X values that you're going to use, and that's going to help you when it comes to graphing. So those first two, all that we really did, this first one, we only did a horizontal shift. The second one, we did do a horizontal shift with an amplitude, so with a vertical stretch or shrink. But I used method 2 on both of those. These last two that I'm going to do, they're a little bit more complicated, so I'm going to use that method 1. And I don't really want to show you the answers because I want you to see. So I'll make my screen a little bit bigger and a little bit more centered. Actually, let me cover up right here. Yeah, it doesn't cover everything, but it covers most of it. So you can see the basic equation and what it's going to ask us for. It says graph y equals 3 minus cosine or 2 cosine 3 of x. So there's a lot going on. And then it says, not only are we going to do that, but we're going to graph it over 2 periods. You do want to be careful about how many periods it wants you to graph it over, especially if you are manually graphing it on the MyMathLab or on a test. Because if you only graph it over 1 period and it asks it for 2, then you're going to get it wrong. So we have y, that is not a very good marker. Try this one. There, that's better. Y equals 3 minus 2 cosine 3 of x. That's what we have. And so when we first get going with this, I'd like to identify all of the translations that's going to happen, no matter if I'm using method 1 or method 2. So if I look at this first number, this number is out here. And if we think about the y equals c plus a sine b x minus d formatting, if we think about that really general format, then this 3 corresponds to the c, and that tells me that I have a vertical translation or a vertical shift. And since it's positive, that means I'm going to move everything up 3 units. So that number tells me it's a vertical shift. This next number, this minus 2, that's affecting my A. That's my amplitude. That's my amplitude. So remember, amplitude is the absolute value of A. So in this case, it's the absolute value of -2. So it tells me my amplitude is 2. That's my horizontal, or excuse me, my vertical stretching and shrinking. So we're going to go up to 2. The next number I hit is the 3 that's in here. Notice that corresponds to my B. This affects my period. This is my horizontal stretching and shrinking. So my period is 2 pi over B, in this case, 2 pi over 3. Okay, now I do method 1 wants you to solve it with the absolute values. I do it a little bit more like we did in 4.1, where I think about, okay, we're going to start at 0. We're going to go to 2 pi over 3, and I need to subdivide that section into 4 pieces. And so what I do is I take 2 pi over 3 and I times it by 1/4, and then I times it by 2/4 and 3/4, and then that way I get my different subdivisions that I need for my table. So if I do that, those are my x values. Then I start at 0. Next, I would take 2 pi over 3 times 1/4, which would give me pi over 6. Then I would take 2 pi over 3 times 1/2, which is 2/4, which would be pi over 3. Then I would take 2 pi over 3 times 3/4, which will give me pi over 2. And then I end with the 2 pi over 3. So those are my different intervals. These are going to be my x values that I point in. Now, some of you might be thinking, well, wait a second. It says I have to do it over 2 periods, but this is 1 period. You're right. So here's the nice thing though, is that cosine, if you remember, it starts in the top and it goes down like this. And it is symmetric to the y-axis, which means if we fold our graph from left to right along that y-axis, everything that's on the right ends up on the left. Since it's symmetric, I can do the exact same shape on the left-hand side. And so I could go this direction with these values and it's going to be mirrored. If you're uncomfortable with that, or you're having a hard time picturing the fact that it's going to mirror itself, you could go ahead and do the other period going the other direction. You don't have to, but you could. I think when you see this graphed out over 1 period, you're going to see how to graph it over that 2nd period, and it's not too bad. Okay, so we have our x's. So now the next step would be to find our 3x. Well, 3 times 0 is 0. 3 times pi over 6 will be pi over 2. 3 times pi over 3 is pi. 3 pi's over 2, and then 2 pi. So we've done x, we did 3x, so next we're going to do cosine of 3x. This is where knowing that unit circle becomes really helpful, because then I'm finding, okay, what is the x value on the unit circle for 0? Well, the x value is 1. What is the x value at pi over 2? 0, -1, 0, 1. Like, having that unit circle really does help you go a lot quicker through a lot of these problems. If you didn't know what cosine of 0 was, you could type it into your calculator, but that takes quite a bit longer. So again, I want to strongly recommend that you learn that unit circle. Okay, so we've done cosine of 3x. So now let's apply that -2, or the 2. We don't have to apply the -2, just the 2. So let's do 2 cosine of 3x. I guess you could do -2. The book did 2. That's why I did 2. So we're taking 2 times this row above. So that'd be 2, 0, -2, 0, 2. The last row is where we do all of it. So 3 minus 2 cosine 3x. So I take 3 minus this spot. So 3 minus 2 is 1. 3 minus 0 is 3. 3 minus a -2, that'd be 3 plus 2, which is 5. 3 minus 0 is 3. 3 minus 2 is 1. So there's a lot to do with the table, but the nice thing about the table is this top row is our x values, and this bottom row is our y values. So when it comes to graphing it, that's the information we're going to use. I'm going to try and leave all of that on the board at the same time as I'm graphing. Give a little bit of grace with the graphs. Although I've got a really good graph right there in the notes. 1, 2, 3, 4, 5. And then we're gonna subdivide over here to where we have pi over 6. We've got pi over 3, pi over 2, and 3 pi's over 2. Now that's one period, and that's a period moving in the positive direction. So I'm going to make the other period go in the negative direction. So we have negative pi over 6, negative pi over 3, negative pi over 2, and then negative 3 pi over 2. So I'm moving that direction. Okay, when x is 0, y is 1. When x is pi over 6, y is 3. Pi over 3, we're at 5. Pi over 2, we're at 3. And 3 pi over 2, we're at 1. So over one period, we look like this. Now remember, it's symmetric about the y. So at pi over 6, if I was at 3, then at negative pi over 6, I'm also at 3. If at pi over 3, I was at 5, then at negative pi over 3, I'm at 5. So this is how I'm able to get my second period graphed, is because of the symmetry that I know exists in my cosine function. And that's a lot of work to graph this, but there's also a lot going on in this. It's not just as simple as taking a picture, taking our basic graph and moving it around, because our period's changing and our amplitude's changing, and then we're doing a vertical shift. Like there's a lot of stuff going on. The only thing we didn't do in that one was we didn't have a horizontal shift as well. Like I said, my picture here in the notes is probably a little bit better. I mean, it's the same picture, but it's on graph paper. So that's using more of the method 1 style of figuring out how to do these graphs. Remember, you can use whichever method you want. You can use some sort of combination of the methods if you would like. But there's that. We're going to do one more that has every translation in it that we've learned. So this one, like I said, didn't have a horizontal shift. The next one will. The next one's kind of the Mac Daddy of them. There's a lot of stuff there. I'm going to try and block some of it. So the next one is going to be a sine function. And I didn't realize I could put the sine one up there instead of the cosine one, but I think you'll forgive me on that. All right, let's erase all this information. All right, this time we are graphing y equals -1 plus 2 sine parentheses 4x plus pi over 2 periods. So we're going to do 2 periods again. But one thing I want you to notice, because it can slip by pretty easily, is that when you look at the problem we're doing versus this general form up here, notice that the general form, that B for our horizontal stretching and shrinking that affects our period, is outside of the X and that D. And so what that means is it's not just looking in here and saying, okay, well, that 4 is outside of the X, that 4 is my B. That's not correct entirely, because that 4 has nothing to do with that pi. What we have to do is we first have to factor out that 4. Okay, so instead of this equation, I'm going to actually think about y equals -1 plus 2 sine, and then I'm going to make a bracket, and I'm going to pull that 4 out. so that I have 4 times x plus, if I divide pi by 4, then I have pi over 4. Now I have an equation that is mirroring this basic function that we start with. That step of dividing out that 4, as you can see right here above the video, is super important because it can slip by, because that 4 is the amplitude, like it doesn't, not the amplitude, excuse me, the B, which affects our horizontal shifting with our period. But if you don't factor it out, then what's going to happen is your horizontal shift is going to be completely wrong. Because if I don't factor that 4 out of the pi as well, then I'm going to think, oh, I'm moving everything to the left pi units. And that's not what's actually happening. I'm only moving things to the left by pi over 4 units. And so you do want to be really careful about that. Okay, so I have it written just like our general function thing. I'm going to note all of the different translations that are going on. You don't have to do this when you're doing your problems. Like I said, it helps me, and so I like to note what's going on. This -1 tells me that I'm going to do a vertical shift down 1 unit. This 2 is what affects my amplitude. And so amplitude, again, is the absolute value of A. In this case, it's the absolute value of 2, which is 2. Amplitude is a vertical stretching or shrinking. This 4 inside of here, that's connected to my B. That affects my period. Remember, period is 2 pi over B. So in this case, it would be 2 pi over 4, which is pi over 2. The last number is this pi over 4, and it's positive. This is a horizontal shift where we are moving to the left pi over 4 units. So all kinds of stuff going on. All kinds of stuff. And since our period is so small, then when we subdivide that into 4 different units, we're also going to get small units. So there's all that information right there on the notes. So in order to divide our period into 4 equal parts, we start at 0 and then I'm going to take pi over 2 times 1/4, which will give me pi over 8, times 1/2, which is pi over, or 2 pi's over 4. That'll be pi over 4. 3 pi's over 4 will give me 3 pi over 8, and then pi over 2. So those are my intervals for 1 period, but I have to do my interval, or excuse me, I have to graph this over 2 periods. So like I said, you can think about this if you want to with the negative intervals as well. I could think about negative pi over 8, negative pi over 4, negative 3 pi over 8, and negative pi over 2. You could even go so far as to, when you're doing your table, if you're doing your table with this, you can include all of those values. Instead of just finding the values for 1 period, you could find them for 2. Obviously that makes your table ginormous, but you could totally do that. I like to think more along the lines of symmetry and how is the sine function symmetric, and just keep following that, because I think that's a little bit easier. There's less math involved, and I love math, but sometimes you don't need to do 8,000 things of math. Okay, so there's our intervals. Those are going to be our x values. The table for this is kind of large, so I'm going to show you my table. I'm going to keep scrolling up so you can see each level. I don't know why there's a reason for me to put it on the board. So let's scroll up. There's our x's, and I'm only doing it over 1 period. So I have my pi over 8, my pi over 4, sorry, my 3 pi over 8, and then pi over 2. The next row, you're doing what's inside of your function, which is the x plus pi over 4. So I take the row above and I do whatever I need to it, which is in this case, adding the pi over 4. 0 plus pi over 4, pi over 8. Again, you do have to be decent with your fractions. And if you're not at this stage, you need to get there. So again, from Math 20, we spent a whole section on fractions, adding, subtracting, multiplying, and dividing. There's no shame at all in going back and reviewing that material. That's in my YouTube site. If you go to my beginning algebra playlist, it's 1.3, and you could get a refresher there. So, sorry, every time I move across the video, it does that. So for row 2, I added pi over 4. That's my horizontal shifting. The next one, I apply my B out front. That's my horizontal stretching and shrinking. That's what affected my period. And so I multiply, notice every row, like I'm doing one additional thing, which is kind of why I like the table, because you're not doing 80,000 things at once. You're just doing one thing at a time. So I take everything from that row above it and I multiply it by 4. And that gives me the pi, the 3 pi over 2, 2 pi, 5 pi over 2, and 3 pi. Next, I'm finally going to take the sine of all of that stuff. Again, this is where knowing that unit circle really comes in handy, because the y value is what the sine is. So sine of 0 is the y value of 0 on our unit circle, which is 0. So we have 0, -1, 0, 1, and 0. Next, we take the amplitude times that sine function. So 0 times 2 is 0, -2, 0, 2, and 0. Last but not least, we finally do our vertical shift. So we take -1 plus the row above. So 0 plus -1 is -1. -2 plus -1 is -3. 0 plus -1 is -1. 2 plus -1 is +1. And 0 plus -1 is -1. So all of that information to put on our graph. So remember that top row, that X row is your X's. That's your subdivided period. And then you have your Y's as well. Now that's just one period. So you want to do the negative side of your graph as well. So don't forget and just do one period, because it did ask for 2. So I'm going to have pi over 8, pi over 4, 3 pi over 8, and pi over 2. And then I'll have their negatives. Negative pi over 8, negative pi over 4, negative 3 pi over 8, negative pi over 2. And then my amplitude, or how high up and down I'm going to go based on what my y's are from 1 to -3. So 1, 1, 2, 3. All right. So there's all of that. Now, where's my blue? Based on our table, when X is 0, Y is -1. When X is pi over 8, Y is -3. When X is pi over 4, Y is -1. When it's 3 pi over 8, we're up to +1. And then we're back down to -1. Okay. Now, if we kept going in this direction, we would be back down at -3, then back up at -1. You know, it keeps going in that same pattern, which means if we move to the left, it keeps going in that same pattern. So if I'm at -1, the very next thing I would be at would be +1. And then I would be down here at -1. And then I'd be down here at -3, and then back up at -1, so that I could finish my second period of my sine graph moving towards the negatives. And that's what I meant by sometimes it's nice to just do the first period when you're doing your graph and then apply what you know about the symmetry of either the sine or the cosine functions to finish out the other side. Like I said, though, you could very easily have made your table instead of only including the values from 0 to 2 pi, you could have included in your table all the way from -2 pi to +2 pi, and then you just plot those points. You're going to get the same graph regardless of which way you decide to do it. But that is the end of the 4.2 material and all the different translations that we are doing with the sine and cosine functions.